This is question number 37 from chapter 23. It reads, the critical angle for a certain liquid air surface is 47.7 degrees. What is the index of refraction of the liquid? It's a pretty straightforward problem on critical angle. I'm just going to bring in a PhET simulation that might help understand this. So this PhET simulation allows me to look at this in a bunch of different ways. If I turn the flashlight on, we can see that this behaves as a wave. We can see the wavelengths changing. Notice that these wavelengths are closer together in the more optically dense medium, so the speed of light decreases here and the wavelength also decreases. The frequency is the same, and then as soon as it speeds up, the wavelength gets a little bit further apart. I can look at that in a waveform, or I can look at it in this way as an array, much like the lasers that we've kind of looked at in our class already. So in this particular one, I'm going from, I can change the index of refraction. I'm going to make it water here. So now I have water, and as I move this, we'll see here that at this boundary layer, some of the light refracts. Notice it's refracting away from the normal line here. So this angle of incidence is less than the angle of refraction. And some of the light is reflected. And as long as I'm less than a critical angle, I get transmission across the boundary. However, at some point here, and we see as the refracted ray gets closer and closer to 90 degrees, this is the refracted ray, as it gets closer and closer to 90 degrees, I get less and less transmission, and then at 90 we can say that all of the light here is refracted. Now I could basically grab this thing and attempt to measure it if I were doing this in real life, but this is just to kind of illustrate the effect. So again, in this case, it looks like just shy of 50 degrees would be the critical angle here, and then anything less than 50 degrees and I transmit across the boundary, anything greater than 50 degrees or that critical angle, 50 something degrees, and it's totally internally reflected. That's what this kind of phenomenon is known. So let's go ahead and bust out some Snell's law to help solve this problem. Snell's law, something you should know, is Ni, the incident side, sine theta I is equal to Nr sine theta R. Everything on the right-hand side is the refracted side. Everything on this side is the incident side. It's important to keep this straight because I'm starting in the liquid and then I'm going into air. So if you reread the question, you'll see that this is a liquid-air boundary. And we're only going to get a critical angle going from the more dense medium from liquid to air. So if you reverse these and you make the air the incident side, this won't work out for you. So make sure you keep everything straight. So we're looking for the index of refraction of the liquid, which is going to be this guy, the index of refraction on the incident side. The air side, of course, is 1, and everything else is known. So the next step would essentially be to substitute. I can say that Ni times the sine of the incident angle, which in this case is 47.7 degrees, is equal to the index of refraction on the refracted side, 1.00 is the index of refraction of air, times the sine of 90 degrees. The sine of 90 is 1, so basically everything on the right-hand side is just equal to 1. That makes this pretty easy, and so therefore the index of refraction is going to be 1 over the sine of 47.7 degrees. Make sure your calculator is in degree mode when you do this kind of stuff, and you get 1.35.